This one is going to feel like a retread from the previous video, and that's because it is. I wanted to mention something at the end of this one that I did not get to in the previous video. So we've got the function natural log of x. We're going to do Taylor series again, centered at 1. And what we did in the previous videos, we started with our original function, ln of x, and then we took several derivatives just to try to give us a good chance at writing a pattern. So natural log of x, take its derivative, 1 over x, take that derivative, negative 1 over x squared, taking that derivative is 2 over x cubed, and so forth. So I ended up taking like 5 derivatives, and each one of these, the original function and subsequent derivatives, because the center is at 1, substitute 1 in for all of them. Take your time, make sure your calculations are good. Our first term was 0, but after that, we started having some actual numerical values we could put in our numerator, and we could actually keep a term. So remember, when you start building your series, it's the function value starts it off, and then you have 0 factorial as its denominator, and then x minus 1 to the 0, and then you move to your first derivative, and it's first derivative value over 1 factorial times x minus 1 to the first, and you keep building on from there. Let me go ahead and scroll. There we go. Now, if we had a Maclaurin series where the center was 0, we would have plugged 0 into all of those functions and subsequent derivatives. We'd have got some different values. But with a Maclaurin series, remember the center is 0, so it's just a single x term. It's not x minus 1. This would have been your Maclaurin series, the way you would build it. Notice your denominators, they're consecutive factorials. The numerator alternates sign as you go, and so forth. With a Taylor series centered at 1, then you have x minus 1. Notice here in blue, the factorials, remember, like 2 factorials, 2 times 1, 3 factorials, 3 times 2 times 1, but you could cancel and it would leave a 3. This black row of terms here, these new numbers in the bottom, those are if you take your numerator and reduce it into the factorial denominator. So as you can see, with a Maclaurin series, this is the black ink. You'd have, after you eliminate that first term, you would have x minus 1/2 x squared plus 1/3 x cubed minus 1/4. And again, that's if you take 6 and reduce it into 4 factorial, you get a 1/4, x to the 4th, and so on. With a Taylor series, we have x minus 1. Notice your terms will stay pretty well the same. It's just your x term has got that minus 1 in there. When we built our infinite series representation, our function, natural log of x, as an infinite series, we have sign alternating in the numerator, plus minus 1s. We had consecutive numbers in the denominator, a 1, 2, 3, 4, 5, and so forth. And then we had x minus 1 to consecutive powers. The denominator and the power always matched, and so those are both in, starting with the first term and not the 0 term. The 0 term eliminated and went to 0. What I did mention in the first video is that suppose I only take the first 3 terms out of this series, and this is up here in red. I'm circling it with this highlighter. X minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. Now, if I stop there, I have a third degree polynomial approximation of the function natural log of x. Now, what I want you to do, if you have a graphing calculator handy, is pause the video here in just a second. I want you to go into your y equals screen, And on the first line, I want you to put natural log of x. Hit enter, and then on y2, the second line, carefully enter this third degree polynomial. When you hit graph, the calculator will graph natural log of x first, and then it's going to graph this third degree polynomial. They'll look a little different, but at 1, they'll be identical. And then as you stray left and right away from x equals 1, they'll start to look a little different. But there's a small window of time where you can't tell this function, this third degree function, apart from the original function. They'll look almost identical for a short period of time. In the previous video, we used a Maclaurin series to build a representation or infinite series for sine x. Let's do it for cosine. Cosine x, we take our original function, and then we do subsequent derivatives. Every time you get to the fourth, you have a repeat. Maclaurin means the center is at 0, so substitute 0 in for all these x's. And we've got 1, 0, -1, 0, 1, all the way through. Using these function and derivative values, we can start building our infinite series. 1 over 0 factorial x to the 0 plus 0, 1 factorial x to the first, minus 1, 2 factorial x squared, 0, 3 factorial x cubed, 1 over 4 factorial x to the fourth, and 0 over 5 factorial x to the fifth. Every other term goes to 0, and if you go look at the other video, or if you remember with sine x, every other term also went to 0. What I want to get to in this video, it's a little bit different, is we keep all the even-powered terms. What do I mean by that? Notice how the x squared survived, the x to the fourth survived. If I had built a -1 over 6 factorial x to the sixth term, that term would have survived. I have sign alternation each time I go. I've got positive, negative, positive. If I had built that sixth term out here, I'd have a -1 over 6 factorial x to the sixth. So when we build our infinite series, we have the sign alternator. Now it needs to start with a positive, so I'm going to use 0. -1 to the 0 is +1. 0 factorial x to the 0. But because I'm only keeping even terms, I have to use this kind of term, 2n. If you double any number, it's going to be even. And so that's the trick to making sure you always get an even value, is use 2n. Back to the blue boxes. I stopped when my power got to 4. If I had gone out here where my x to the sixth term exists, and I used all of them, I'd have a 6th degree approximation. But I only stopped here at 4. So let's look down in the blue ink. Everything you see in the blue ink, I've transferred it down here. That highest power, that's the degree. So this is a polynomial of degree 4 with a variable x. So p sub 4 of x. Take the value from each of those blue boxes, rewrite them. This is a 4th degree polynomial representation of a trig function cosine x. Now, like in the last example, if you need to pause the video for a little bit, feel free to. Go back into your y equals screen, put cosine of x in your y1 line, carefully type this polynomial into your y sub 2. And then when you graph, I would recommend to be in radian mode because it's a trig function. I'd recommend to be in radian mode and maybe hit zoom 7 to do a zoom trig setting. Once you've got that going, your cosine curve, of course, it just oscillates up and down, up and down. For a small window of time, And because this is a Maclaurin series, if you'll look close to where the y-axis is, where x is 0, now notice if x is 0, it's exactly cosine, because if you replace these x's with 0, all you're left with is 1. So p sub 4 of 0 just gives you 1. Cosine of 0 is also 1. So at the center, they're exactly the same. But as you go left and right, and you stray left and right of that center, this fourth degree polynomial is pretty darn close to that trig graph of cosine x. The longer you make this list of polynomial terms, if I'd gone to the sixth or even the eighth, you couldn't distinguish the graphs near the center. As you go further out left and right, you'll start to see some discrepancies. But near the center, at the center, they're identical. Near the center, it's hard to distinguish one from the other. And so this is just how you would approximate natural log in the first problem or cosine of x in this problem. You can approximate them with a polynomial. The more terms, the better. And so anyway, I didn't want to overkill these two problems, but I definitely wanted you to see that you can use these infinite series to generate some terms that represent your original function pretty well.